Yes, I can. Yeah, thank you.
All right, perfect. Thanks for the confirmation. So STP or Spanning Tree Protocol, this is one of the important topics of switching part of CCNA. And this is something you will see that if you understand well, then it can help you a lot in later in CCNP and CCIE level as well, because STP is everywhere in all the certifications in varying details, of course, but the basics should be clear on the CCNA level. So we are going to understand in very simple structure, what is STP, why do we use it, and of course the last and the biggest question, how do we configure it or tune it, right? So first thing first, what exactly STP is? So STP is actually a loop prevention mechanism. So what it does is that it prevents loop while maintaining redundancy. While maintaining redundancy. So what do we mean by this statement that it prevents loops while maintaining redundancy? So to understand this, let's take an example. Let's say we have a switching network where we have a few switches. Let's say switch 1, it is connected to switch 2 and switch 3. So in this diagram, we can see that we have connectivity between these switches. And if you have some devices connected to switch 1, switch 2, and switch 3, these devices can communicate to each other because there is connectivity. So you can go from any switch to any other switch. As we can see, there is a way to reach from every switch to every other switch. But there is only one way, only one route to reach from any switch to any other switch. There are no backup routes, right? For example, so from switch 2, if I want to go to switch 3, the only way is via switch 1. There is no other way in this particular diagram, right? So when you have a structure like this where you have only one way to go somewhere, we call this a tree structure, right? It's a tree structure, and the benefit of this tree structure is that you don't have a possibility of looping, because something goes from switch 2 to switch 1 and from switch 1 to switch 3, it cannot come back to switch 2 because there is no connectivity between switch 2 and switch 3. And the switches have this rule that any traffic received on a particular interface is never sent back out the same interface. So if switch 3 receives something from switch 1, it is not going to send it back to switch 1. So there is no way to bounce it back the same way. It could go from switch 0 to switch 2 if there were a link, but since there is no link between switch 2 and switch 3, this is called a tree structure. Only one way to go from anywhere to anywhere else. So this is inherently loop free, right? When you have a tree structure, it is inherently loop free. But the problem is with the tree structure is that this is non redundant. It is non-redundant, means there is no redundancy, there are no backup links between any switches. So what happens when you have a non-redundant link or non-redundant network? The problem is that there is no fault tolerance, right? Because if there's a fault somewhere, let's say if this link goes down between switch 1 and switch 3, what will happen? There will be partial disconnectivity into your network. Like switch 3 will have absolutely no connectivity to any other switches. There are no other ways to go to them, right? So switch 1 and switch 2 cannot go to switch 3 and vice versa. So you have partial disconnectivity now because there was a fault in your network. So this is called no fault tolerance. So the benefits of tree structure is that it is loop free, but because it is non-redundant, the drawback is that there is no fault tolerance. And administrators do not like this. They'd like to have fault tolerance as much as possible. Why? Because nobody would like to wake up in the middle of the night getting a phone call from the company that there is a problem in the network, like partial disconnectivity. Some people or some nodes cannot connect, and you have to troubleshoot it at that time. Maybe from there, maybe you have to go to the office, right? In the worst case scenario, nobody would like to do that. Especially network administrators, they like to have as many backup links as possible so that they don't need to act immediately, and the network doesn't have any downtime because of some kind of fault, right? So what they like to do is they like to go ahead and connect as many backup links as possible. Like if we can connect switch 2 to switch 3, what happens with this is that now you have two ways to go anywhere. Like from switch 2, If I want to go to switch 3, I can go via switch 1, or I can go directly switch 2 to switch 3, right? And you can check this from any other switch. We have two routes now to go to any other switch now. So when you have this kind of network, this is called redundant network and or redundant structure. And when you have the redundant structure, the benefit that you get is that now if there is a failure somewhere, let's say if this link goes down, you still have full reachability, because from switch 2 you can go to switch 3 directly, and if you want to go to switch 1 you can go via switch 3, right? So there is absolutely no downtime as far as communication is concerned, and then you can troubleshoot, you can fix that issue without people calling you, sending you emails, or asking you why the network is not working, because it is still working completely fine, right? Of course, you can go ahead and create as many backup links as you like. Maybe you have couple of links between every switch like this. In this case, you have more redundancy now. Now, if two links go down also, you will not actually have any issue. You can have three links as well. You can have more links like this. So basically, the more redundancy you have, the more fault tolerance you will have, right? So redundancy actually give you directly the fault tolerance. That's the benefit you get, right? So the benefit of tree structure, where you only have one way to go somewhere, is it is loop free. But the drawback is that it is not fault tolerant because it is non-redundant, right? But redundant structures give you the benefit that you have fault tolerance, but now you have an issue of looping. So there is a possibility of looping here. How that can happen? For example, if switch 2 receives some traffic which is supposed to go to a MAC address connected to switch 3. But now this computer which had the MAC address is no longer connected here. So switch 3 has removed the MAC address from the MAC address table. So switch 2 will send the traffic to switch 3, thinking it's connected to switch 3. But switch 3 now no longer have that MAC address because it has removed it due to the disconnection of this computer. So switch 3 will say, okay, I'm receiving the frame for an address which I don't know. And what do I do with the addresses I don't know? I do unicast flooding, right? I flood it everywhere except the port where I received it. So I will flood it everywhere, including this trunk port. Switch 1 will receive it. Switch 1 will say, I don't know about this network, so I'm going to flood it everywhere except the port where I received it. So I will send it to everyone, also to this trunk port. And you can see we are back to square one. Switch 2 will say, okay, I'm receiving some frames which wants to go to this particular MAC address. So I'm going to send it to switch 3, right? So this will continue. So this is called looping. And the problem is that unlike routing, in the switches, you do not have any TTL kind of concept, right? The time to live kind of concept, where you can stop after some time. So in the routing, what happens in a packet, you have a TTL field which is set to 255. And when the packet goes router by router, when it is going somewhere and it is crossing multiple layer 3 devices, it is going hop by hop, every router is decrementing this number by 1. So you go to the next router, it makes it to 54. Then the next router, it makes it to 53. So if your packet is looping in a routed environment, this number will eventually become 0. And as soon as it becomes 0, the packet is dropped. So your packet is not going to loop infinitely into a routed environment if you have a routed environment, right? So TTL actually helps you stop any potential looping after a certain point. But in frame, if a frame is looping between the switches, there is no TTL field into the frame, right? So it will, if it is looping, it will keep on looping indefinitely. There is no way to break it unless you physically introduce a break somewhere, like you remove some certain cable, then only it will be possible. So why is it happening? Because we have introduced redundancy, because we have introduced more than one ways to go somewhere. Now you have a possibility of looping. So you see that we want to have the benefits of backup links, but that brings us with the burden of looping, and that's why we cannot maintain the redundancy, we cannot maintain the backup links. We have to remove the backup links so that there is no looping, and now we have the problem of no fault tolerance. So that's where STP comes into the picture. STP says, you know what, go ahead, and connect as many backup links as you like, and I will make sure that the loops do not happen, the looping do not happen, right? So that's why the definition of STP is that it prevents loop while maintaining redundancy, right? Excuse me. So SCP says you can make your network redundant. So we are happy now because we have many backup links, and we are also more happy because there is no looping thanks to STP. So how does STP do that? That's what we will learn. But what is STP? STP is a protocol which prevents looping in the switching environment while maintaining redundancy. Why do we need this? Of course, that's obvious because loops are very bad. The loops can actually cripple your network. If the if you are sending a broadcast or multicast stream which has no destination, it could be actually huge in bandwidth consumption also, and then it make your network very slow and your switches very slow. So nobody wants to have loops, right? So why do we use STP? It's very easy. We want to prevent the loop. Now comes the question: this how does STP do that? How does STP prevent loops in this case? So actually, the idea is very simple. STP says, which can guarantee 100% loop-free network? A tree structure, right? If I have a tree structure, it will be loop-free, guaranteed loop-free. There is absolutely no possibility of looping. So that's what I'm going to do. I'm going to make it a spanning tree structure because it is spanning starting from a single device. Like if you see an upside down tree, we start from the root and then we have the trunk and then we have the branches, right? Similarly, we will start from a root switch and then there will be other switches, and we will make sure that there is only one way to go from any switch to any other switch. If there are any backup links, if there are any redundant links, I am going to block them. That's what STP does. So STP just makes it a tree structure, and that's why it becomes loop free. Simple as that. Now you must be thinking, okay, hang on a minute. You are telling me that STP is going to make it a tree structure, which has the big issue of no fault tolerance. So then I don't want it. I want fault tolerance, right? So I just don't want to stop looping. That I could have done myself. I could just remove the cable between switch 2 and switch 3, and this network will become non-redundant, right? Then I don't need to worry anything about looping. I don't want to do that. That's why I need some protocol. So STP says, hang on, that's what I'm doing. I am going to make it non-redundant. I am going to make it a tree structure, but I will keep an eye on the network. And if there is a fault somewhere, I will re-enable that so-called backup link because now some other link is down. So I still follow the tree structure because let's say if this link goes down, first of all, STP will decide one of these links to be blocked, right? So let's say STP has decided this link I am not going to use, right? This link is blocked. So if this link is blocked, we are not using this link anymore. That means we have only path via switch 1 to go to switch 2 and switch 3. So this network has become tree structure. Now STP is keeping an eye. So if this link goes down, STP will immediately unblock this link, right? This link will be unblocked. And once this link is unblocked, you still have the complete connectivity. So this all happens automatically. So you do get fault tolerance while having absolutely no issue of looping, because at any point of time, your network never have backup links. You will always have a tree structure, because if there are any backup links, any redundant links, STP is going to block them, right? And don't worry, STP is keeping an eye on the network. If something happens somewhere, it is going to re-enable those links, and you still have full reachability, right? That's how STP works. Now, for that, STP has to find out all the backup links and then have to block them. And that's exactly what STP does, right? But let's say that for the sake of this example, we have three links here: one link between switch 1 and switch 2, one link between switch 1 and switch 3, and one link between switch 2 and switch 3. So let's say STP has decided to block the link between switch 2 and switch 3. This link, it has decided to block this one. It could be any other link also, but let's just, for the sake of example, let's say this one is to be blocked. So, you know what happens when you want to block this link, means you don't want to use it for any kind of traffic. You don't need to shut down, or you don't need to disable ports both side of the link, right? If even one side I block it, let's say on switch 3 side, I block this port, then technically this link is unusable now. Although switch 2 side, it is still completely operational port, because if switch 2 sends something, switch 3 will not accept it, and switch 3 will not send anything to switch 2. So basically this link is unusable, right? So as a matter of fact, STP doesn't even need to block multiple ports on a backup link. It just need to block one port on the backup link. So out of two ports, which port are you going to block? That's what you need to find out, right? That is called, we call it the least desirable port. Least desirable port means that port is not as good as other ports, and that has to be blocked, right? So the whole STP procedure is actually revolving around this particular point. So you can have another definition of STP as well. You can say that STP, what is the objective of STP? STP finds the least desirable port and blocks it. That's what STP does. If there are more backup links, more least desirable ports will be there and more ports will be blocked. But per backup link, per redundant link, we block one port, which is called the least desirable port, right? So here we are going to find the least desirable port and block it. But the question is, of course, the $1,000,000 question is that which port will be the least desirable port? Because I can see here there are 6 ports, 1, 2, 3, 4, 5, 6 in this diagram. So how does STP find out which port is the least desirable to block it, right? So what STP does, just like any other computing mechanism, it uses numbers to compare between switches and numbers to compare between ports, that which switch is better and which port is better, right? So there are parameters defined by STP, numerical parameters, of course. Some are on the switch level and some are on the interface level, right? So let's talk about the switch level parameters that STP has. The switch level parameter that STP has is called bridge ID, which is a combination of bridge priority and the base MAC address of the switch. The reason I'm calling it base MAC address is because you will see that the switch also has a MAC address for every port. Every port has a unique MAC address. But we are talking about the base MAC address, which you can check in show version command if you have the real devices, right? In EVNG, this command will not show you the MAC address because we have a virtualized environment. But in the physical switches, you can check show version and it shows you a MAC address there, which is the base MAC address of the switch, right? So the bridge ID is the priority and the base MAC address. It's a combination of these two things. And what I mean by this is that the priority value is always going to be checked first, and only if the priorities are same, then you are going to compare the MAC addresses. And the rule is lower is better. Lower is better. And this rule, to be honest, you can just remember for the whole of the STP. It's like a gospel of STP. For everything, lower value is a better value. It's very easy to remember in STP, right? But what about this priority? So in the priority case, you will see that this is excuse me. So this is a 16-bit value, and this can be between 0 to 1,440, and the default value is 32768, 32,768. That's the default value. Unless you change it, it is going to be 32768. And of course, if you change it to a lower value, then your switch becomes the better switch than other switches, right? Because lower is better. But when it comes to changing this value, you have to change it in the steps of 4096. Means you can increase it by 4096 or you can decrease it by 4096. You cannot make it any number. Like you cannot make it 30,000 or 50,000. You can make it 0 or 4096 or 8192 or 12288 and so on. So you have to keep on adding 4096 or keep on removing 4096 if you want a specific value that you can use. Otherwise, it will give you an error. The reason they step it like this is because there are 4096 VLANs and we use per VLAN spanning tree, right? We have one STP for every VLAN in Cisco implementation. So you cannot just use any value, yeah, right? And if the priority is same, then only you are going to compare the MAC address. So MAC address is not compared if the priorities are different. Then the lower is better, the rule wins, and we already get our answer there, right? Just a second, just give me a. Sorry about that. I'm back. So this is on the switch level, and then on the interface level, also you have two parameters. Interface level parameter. So first thing is called the, just like you have the bridge ID here, you also have something called port ID, and this is created by the port priority and the port number, right? So the port priority here, it's an 8-bit value, and it could be between 0 to 240. Default is 128. So you can actually increase this in the steps of 16. So you can make it plus 16 or minus 16 like this, or you can keep on increasing or decreasing by 16, but not anything else. And again, the same thing, lower is better. The lower value is always a better value, right? So this one can be used to compare the ports. And if the port priority is same, then only you are going to compare the port numbers. And port numbers are internally assigned by STP. And generally, the lower port number will be assigned lower number, and higher port number will be assigned higher number, right? So you might see different numbers, and you can check it into the show span tree command, what port numbers are assigned. Lastly, the second parameter that is assigned for interface level is called cost. And cost actually is an integer which has default values according to the bandwidth of the interface, but you can change it to anything. There is no rule for the steps of 4096 or 16 or anything else like that. You can change it to any value, but there are some default values. So you will see that in the cost, you can actually use a 16-bit cost, which is called the short method, or you can use the 32-bit cost, which is called the long method, right? So short and long, two different types of cost are supported. Like you will see that for very high speed interfaces, using the long method is better because you can have more distinction between the different cost of different interfaces. Normally default is the short method, right? So you will see that depending on the interface bandwidth, you will have either the short cost or the long cost differently configured, right? So depending on the interface bandwidth, you will see different cost values. For example, if your interface bandwidth is 10 Mbps or 100 Mbps or 1000 Mbps, or let's say even 10,000 Mbps or 10 gig per second, 10 gigabyte per second interfaces, you will see that in the short method, you have the cost 100, 19, 4, and 2. So as soon as you go to the very high speed interfaces, you don't have much space now because you have to go lower and lower. So like if you have 100 gig interfaces or Ether channel with many 100 gig interfaces, it's not even possible to distinguish between them using the short method cost, right? There is no space. That's why they created a longer method with 32-bit value. So for that, 10 Mbps ports will have the cost of 2 million. Right? 100 Mbps ports have the cost of 200,000. and 1000 Mbps ports at the cost of 20,000, and 10 gig ports or 10,000 Mbps ports at the cost of 2,000. So you can see that you still have space for more even higher speed connections if you're using the long method. But these are the cost values that we use. Now the thing is that you have the switch level parameters like bridge ID and interface level parameters like port ID and the cost. They can help you to find the least desirable port. So how it starts working is that first of all you choose a root bridge. The root bridge is like, if you think about a tree structure, an upside down tree, it starts with a root, right? So you have to start from a root. You have to start working from one switch, which will be considered the root bridge. And the reason we have to select that and start working like that is because we want to find the least desirable port, right? So first thing first is that what happens is that the root bridge is elected, right? Root bridge election. So the root bridge election simply happens by comparing the bridge IDs. So the switch with the lowest bridge ID, becomes the root bridge, right? So for example, the bridge ID is the bridge priority and the base MAC address. The bridge priority is by default 32768 and the MAC address is the switch MAC address. So let's assume that all of the switches have the same priority 32768, and let's say the MAC addresses we are using are A, B, and C. So in this case, because the priorities are same, we are going to compare the MAC addresses, and switch one has the lowest MAC address A. So switch one becomes the root bridge, right? Like this. So we will have a root bridge election. And remember, we want to find that which port to block. So we actually work same in similar way like a murder mystery, like who done it kind of movies, where you have multiple suspects and you want to know who is the killer. So what do? If you are a good detective, you are going to start eliminating people that who cannot be the killer, right? So you start eliminating. So your number of suspects or the scope of number of suspects will shrinken, and you will have less and less people into the suspect list. Like, okay, you cannot be the killer because you are out of town. You cannot be the killer because you had a strong alibi, and so on. So you start removing people, and then you end up with the killer. Similarly, I have 6 ports here in this diagram. I want to block one of them. So what do? I decide, or I find out the interfaces which are definitely not going to be blocked, and I start removing them, and that way hopefully I will end up with one interface which will be blocked. So what happens is that as soon as we have a switch elected as a root bridge, you will see that all of its ports are considered or configured as the designated ports. Let's call them D, and these ports are never blocked. So you can see that all the ports of the root bridge are out of the suspicion. They cannot be blocked, right? So we have 2 ports less to worry about. Now we only have the ports on switch 2 and switch 3, 2 ports each, total 4 ports. We have to find out which port we are going to block there, right? So all the ports of the root switch become designated port, and designated means they will never be blocked. So you will see that these are called the port roles. So the port roles are designated, which simply means the downstream port. And what do I mean by downstream? That means going away from the root bridge. Going away from root bridge. So any port that takes you away from the root bridge or not on the best path toward the root bridge, then that is called the designated port. And this is the best port on the link. It's the best port on the link, on the segment. So a link has 2 ports, right? Every link is connecting 2 ports. So between switch 1 and switch 2, we know that switch 1 is the better switch. So of course, that's why it has the better port. So on that link, switch 1 side port is a better port. That's why it is already designated, as you can see. All the ports on the root switch are designated. And anyway, of course, every port of the root switch takes you away from the root switch. That's why it's a designated port. It's a downstream port, takes you away or further from the root bridge. and it is the best port on the segment. That's why it is called designated. And why it is important to know designated port? Because this port is never blocked. This port is never blocked, right? So on the root port, we will never block, on the root switch, we will never block these ports. And then what happens? The root switch will start sending a tiny frame every 2 seconds, which is called hello interval. And this frame is called BPDU, Bridge Protocol Data Unit, right? So point number 2 here is that once the root bridge is elected, all ports of root bridge are designated. All ports of the root bridge are designated and never blocked. And never blocked. So that is something we saw. And then, of course, this is the benefit you get of becoming the root bridge. So, of course, with the great power comes great responsibility. So now you get the power that none of your ports will be blocked. But now you have a responsibility. And what is the responsibility? That the root bridge starts sending a periodic hello, right? The root bridge starts sending a periodic frame, which is called BPDU, Bridge Protocol Data Unit. And periodic means what? Every hello interval. So there is a hello interval configured by default set to 2 seconds. So every 2 seconds you are going to send a tiny frame which is called BPDU, right? Per STP. So for every STP instance, you are sending a BPDU. So what is the benefit of this? Because remember, on the root switch, we already know the designation of the interfaces, the role of the interfaces. Like all ports are designated ports, right? But what about switch 2 and switch 3? What kind of ports do they have, right? So remember that every other switch has to have a special port, which is called the root port. The root port actually allows you to go to the root switch. It's an upstream port as contrary to the designated port. Designated port takes you away or further from the root bridge, or it's not on the best path to the root bridge. On the contrary, root port is on the best path toward the root bridge. It's an upstream port. So they need to find at least one port, not actually at least one port, only one port, which will be the root port toward the root switch. So you see that the root switch itself never has a root port because root port takes you to the root switch and you are the root switch. So you don't need a root port. But every other switch will have root port and you cannot have more than one root ports every switch, right? So that's the second port role, which is called root port. And root port simply means it's an upstream port, takes you toward the root bridge. And this is actually on the shortest path, on the shortest or the best path toward root bridge, right? So every switch will have a root port. Every non-root switch except the every switch will have the root port basically except the root bridge itself, and only one port, only one root port per non-root switch. You cannot have more than one, right? But the benefit of root port is also is that it is never blocked, never blocked. So how do we actually find out which port is going to be which port is going to be the root port, right? So to find it out, this BPDU is going to help us. That is coming from the root bridge. So what happens is that this BPDU that is coming from the root bridge, it contains some very interesting information. It contains the information about the root bridge, that who is the root bridge. So one section will tell you the root bridge information, right? Second part of this BPDU will tell you the sender bridge information. What do I mean by sender bridge? So sender bridge simply means that the switch which is sending me this BPDU. So what happens is that the BPDU is sent by the root bridge, yes, but it can be propagated by other switches. So maybe switch 1 is the root bridge, sends it to switch 2. Switch 2 can send it to switch 3. When switch 2 sends it to switch 3, it still says that the root bridge is switch 1. So the root bridge information is about switch 1. But because the sender is switch 2, the sender information changes to switch 2, that I am the one who is sending you this or propagating this BPDU to you, right? So that's why there are two information. And then comes the most important thing, the path cost. What is path cost? It is actually the total cost of the path. So you actually add the interface cost to the BPDU as it is traveling through the network. So you'll see that it starts with 0. It starts with 0. And what happens is that every inbound interface cost is added to path cost. So not to be confused, this is not the interface cost. You add the interface cost to the path cost. And which interface? Every inbound interface. Means when you receive the BPDU, that time you are going to add the cost. When you are sending the BPDU, if the BPDU is leaving the port, you do not add the cost. If the BPDU is entering the port, that time you add the cost. Very, very important distinction. And this can actually help you to find out which of your port is the root port, right? Let me give you an example here. Like in our diagram, switch 1 is the root bridge, and we have switch 2 and switch 3, right? And then there is a connection here as well. So we know that on switch 1 side, because it's the root switch, all the ports of the switch 1 will be designated. So this is the root switch, and all the ports on root switch are designated ports, so D ports. Now, root switch starts sending BPDUs every 2 seconds, and initial path cost is 0, right? When you send the BPDU, initial path cost is 0. And let's say that we are using all 10 Mbps ports. So we know that the cost is by default 100 of every port. So when root switch is sending the BPDU out, are we going to add the cost of this port because we are sending it out this port? No, because when the BPDU is leaving the switch, we do not add the cost, right? We only add it when the BPDU is received. When we are sending the BPDU, the initial path cost is still 0. But when switch 2 receives it on this interface, yes, it is going to add the cost of this interface because you are receiving the BPDU on this interface. So here, the path cost becomes the whatever the cost of the interface added to the existing path cost. Existing path cost is 0 and the interface cost is 100. So it becomes 100 here, right? Similarly, you start with path cost 0 here, but on switch 3, it becomes 100, right? Now, when when switch 2 forwards the BPDU further to switch 3, and this is what I was talking about, that when switch 2 received it from switch 1, the root bridge was switch 1 and sender is also switch 1. But when switch 2 forwards it to switch 3, it changes that information that root bridge is yes, switch 1, we all agree, but sender is myself, I am sending you the BPDU. So sender is switch 2, right? So switch 2 sends it to switch 3, and at the time of sending, are we going to increase the cost? No, because we are leaving the switch 2, so we are going out of the port, so we do not add the cost of this port. But when it comes to switch 3, it is entering this the BPD on this port, so of course we are going to add the cost here. So here it will become path cost 200, right? Because the cost of this port is 100, we add it to the existing cost, which is already 100, so it becomes 200, right? Similarly, when the switch 3 will send the BPDU to switch 2, it has received it and added the cost 100 here, but it is not going to add it here because it is outgoing. But on the inbound port on switch 2 side, yes, it will become 200. Now you can see, think about switch 2. Think from the perspective of switch 2. On switch 2, we are receiving two BPDUs, one directly from switch 1 with the path cost 100, and one via switch 3 with the path cost 200. So which one is better? Lower is always better, right? So that's why this port wins, and this port will be considered the root port. Root port is the port which is on the shortest path toward the root bridge, right? So of course, if the path cost is lowest, that is the shortest path. Same thing for switch 3. Switch 3 is receiving the BPDU from directly from switch 1 with the path cost 100 finally calculated, and one via switch 2 which is having the path cost 200 finally calculated. So I'm going to use the one with the lowest cost, my root port. So that will be my root port, right? So let's clean it up a little bit. Ultimately, what we have received here is this, right? Now you can see that root bridge is selected. All the ports of root bridge are designated ports, and then we elected the root ports on every non-root bridge. And the benefit of root port is that it is also never blocked. So now you can see that we are narrowing down the suspect list. Now we only have these suspects, these two ports, switch 2 and switch 3, and they are one of them will be blocked. So how do we decide that? So what happens is that as soon as the switches know who is their root port, and we know that every switch can only have one root port. So what about the other ports? All the other ports the switch would like to keep as designated, because we know designated is the port which is not on the best path toward the root bridge, but it does have connectivity to the root bridge, and I want to make sure that it is the best port on the segment. So I would like to keep the best port on the segment, right? So switch 2 will say this is my designated port, right? It would like to claim this port as the designated. Same thing happens with Same thing happens with switch 3. Switch 3 would also like to keep this port as designated, because we know designated ports are never blocked and we cannot have two root ports. So you can see that now switch 2 and switch 3 are saying that my side is designated. And remember, designated port is the best port on the segment, and you can't have two best ports. You can have a better one, and that will become the best, right? So that's the last point now that says, and the last point is that only one designated port per link or per segment, as they call it. So you cannot have more than one designated port. That the only the one port which is considered the best will be there. So how do you decide which one will get to keep the designated status and which one will become non-designated? So what happens is that switch 2 and switch 3 will start fighting, and one of them has to win, right? So whenever there is a conflict, we use a 4-step conflict resolution mechanism. Conflict resolution mechanism. And this is like the 4 commandments of STP. Anytime you have to make any decision in STP, you can just rely on these 4 points. And you always check them in this particular order. The first thing you always compare between two fighting entities is who is your root bridge? Who is your daddy, right? So who is your root bridge? And if there's a difference in opinion that who should be the root bridge, of course one of them will win, because lower is better, right? You always take the lowest one. If the root bridge is same, then you are going to compare your path cost to the root bridge. That is of course over the root port. Path cost to the root bridge over root port. If that is also not giving you the answer, then you check the sender's bridge ID. Each other's bridge ID you are going to compare. And if the sender's bridge IDs are also same, then finally you are going to compare the sender's port ID. And that is definitely going to be the last point you are going to check. So you will always definitely going to get the answer at this point. And it is guaranteed that you will get one winner over the other if you go through these 4 points. So here you can see in this diagram, let's say which one is the root bridge, because although the priorities are same everywhere, 32768, but the MAC addresses are different. So this is MAC address A, B, and C. And that's why switch 1 is the root bridge. Now switch 2 and switch 3 are fighting for the designated status on this third link. So they start fighting. First of all, they compare the root bridge. So switch 2 says my root bridge is switch 1. Switch 3 says my root bridge is also switch 1. Okay, then we have the same thing there, so we don't get the result on point number 1. Second thing is path cost to the root bridge. So switch to says that on my root port, my cost to go to the root bridge is 100, right? Because it was 0 initially and then we added 100. Switch 3 says, my path cost to go to the root bridge is also 100 because it was 0 and then I added my inbound port cost. So we both are equidistant from the root bridge. So the cost can help you to find out how far you are, what is the proximity of you to the root bridge, right? And they both are equidistant from the root bridge. So that doesn't give us the answer as well, the path cost to the root bridge, second point. Then we go to the third point, sender's bridge ID. So of course, switch 2 is claiming to be the root bridge. How? Sorry, switch 2 is claiming to be the designated site. How? Because when the BPDU is received, we are forwarding it to switch 3, saying that, hey, I am the designated one. We are setting the designated bit into the BPDU. And switch 3 is doing the same thing. It is sending the BPDU, setting the designated bit and saying I am the better one. So of course they will receive each other's BPDU, which is actually coming from the root bridge, right? But you are the sender. So switch 2 is the sender for switch 3 and switch 3 is the sender for switch 2. So when I say that we are going to compare the sender's bridge ID, what I mean is that we are going to compare switch 2 and switch 3 bridge ID, who has the lower bridge ID. And there you will get the winner, because you can see that switch 2 has the bridge ID 32768 and the MAC address is B, and switch 3 has the bridge ID 32768 and MAC address is C. So first we always compare the priority, which is same in this case. So then you are going to compare the MAC addresses. And of course, MAC address B is lower than MAC address C. So switch 2 wins. And when switch 2 wins, it gets to keep the designated status of its port. That means on switch 3 side, we will have to change it. So on the switch 3 side, it will become non-designated, also known as alternate port, alt port, right? And what happens? It will be blocked, right? Of course, you can change this by changing the priority, because remember, when we are fighting about who is the better one, I can go ahead and change the priority of switch 3 to something lower, uh, which will actually make it the root bridge itself. But let's say switch 1 is the root bridge because its priority is 4096. And here I change the priority to 8192. So switch 3 will not become the root bridge, but you can see it has the better priority than switch 2. So when we come to the third point, when they are fighting, sender bridge ID, switch 3 will win and switch 2 side will be blocked. So you can see, you can control which ports will be blocked or which switch will be the root bridge by changing the priority or changing some other parameters. You can also change the cost of the interface, because you see that on the second point, we compare the path cost to the root bridge. And the path cost over this path is 100 for switch 2, because we add the cost of this port, right? Initially, the path cost was 0. Same thing here, it was 0, and then we add the cost of this interface here and making it 100. So how about if I go to switch 3, this interface, and reduce the cost of this interface to 90? So that's what we will add to the path cost, and it will become 90, which is lower than the switch 2's cost of 100, and you will get the result right there on the point number 2. So you have so many options to tweak these parameters to control which port will be blocked. But having said that, you see that completes our STP convergence procedure, because now you can see that we have a blocking port and then the network has become non-redundant. Again, what is the order of operation? The very first thing that happens is we elect the root bridge. As soon as the root bridge is elected, all the ports of the root bridge are considered designated ports, so they will never be blocked. And the root bridge starts sending a BPDU with the initial path cost 0. Every switch who receives the frame, they receives the BPDU, adds the inbound port cost to the path cost. And when it is sending it further to other switches, it doesn't add the cost of the outbound port, only the inbound port, right? So if a switch receives multiple BPDUs from different locations, it can compare the total path cost, and the lowest one will become the root port. So every other switch will elect one root port, and all the other ports it would like to keep as designated. And if you find any segment where two switches are fighting for the designated spot, they are going to fight who is better, and the one who is better, the one who wins, will get to keep the designated status, and the other one will have to change to non-designated and blocked, right? That's how STP convergence mechanism works. You remember we talked about this in the very beginning, that the objective of STP is to find the least desirable port and block it. That's what STP has done here, right? So as far as the convergence is concerned, the good news is that you don't need to do anything. When you start the switches, STP is already working. It will already find the root page. It will already start working and will block one of the ports, right? So nothing special you need to do. You may want to change its decision if you want to, like if you don't want switch 3 side to be blocking, you want switch 2 side to be blocking, as I mentioned, you can play with the priority or the cost, and you can do that. This is something you will see after the break, and then we will see a lab about that as well, right? So let's just take a small break, and after coming back, we'll see the practical implementation of this. Hey, hi Scott, I'm back. Let me share the screen. Let me know if you can see the screen. All right, perfect. Thanks for the confirmation. Right. So some of the things that I mentioned we can do is to change these parameters. We can change either the switch level parameter like bridge priority. We cannot change the MAC address, but we can change the priority. And similarly, we can change the port priority or the port cost for changing the decision that STP takes in case if you want to have a different solution, right? So here, some of the commands that we can use on the switch level, and some commands we can use on the interface level, depending on which kind of parameters we are changing. So let's connect to one of the switch to see what exactly is the structure. So let's say switch 1. Call it host name, switch 1. So currently, if I check show spanning tree, and let's say for VLAN 1, so because in Cisco we use per VLAN spanning tree, so there will be one spanning tree for every VLAN. So if we just say show spanning tree, it is going to show you the spanning tree for every VLAN, or you can do it only for a specific VLAN by using show spanning tree VLAN 1, and it shows you the structure here. And something happened. Which one stopped responding? Hmm. Okay, so we are on switch 1, and if you check show spanning tree VLAN 1, you can see that it is currently the root bridge. This bridge is the root for VLAN 1. And priority, it always shows you the configured priority, which is 32768 plus the VLAN ID, because it is per VLAN. You have a unique priority because you add the VLAN number to the priority value, which is configured, right? So actually, it is 32768. But for VLAN 1, it will show 32769. For VLAN 2, it is 32770, and so on, right? And the base MAC address is this one that we have on switch 1, right? And the hello time, that how often do you send the BPDU is 2 seconds. And you can see that all ports of the root bridge are designated ports, right? And after some time, they will become forwarding, means they are not blocked. The cost of every port by default is 100 because it is 10 Mbps port. And you can see that the port priority of every port is by default 128. And this is the port number, which is internally assigned by STP. So port priority and the port number. And this is the order you are going to compare them first the port priority, and then if it is same, then port number. Similarly, first you compare the bridge priority, and if the bridge priority is same, then you compare the MAC address. So if you want to change the bridge priority, you can use the command spanning tree VLAN and then VLAN number, whatever it is, priority, and then you can set it some value. So you can see that bridge priority in the increments of 4096. So the idea is that you can change it to a higher value or lower value, but if you are not sure that what can you type, then you can deliberately type something wrong, like 7,000. We know it cannot be 7,000. So it will actually give you all the values. It will say, sorry, allowed values are only these 0, 4096, 8192, 12 to 88, and so on, right? So we can actually configure these values to change the priority. Now, if you don't want to deal with priority, there is some another command also you can use. Spanning tree VLAN1 root primary. If you want to make some switch as the root, or root secondary. So these commands will make sure that one of the switch becomes the root, and the second another switch where you type the command root secondary will become the backup root, basically, right? And on the interface level, if you go to a particular interface, let's say Ethernet 0/0 or 0/1, you can configure spanning tree, VLAN number, cost, and then you can mention some cost. Cost value, you will see, is something that you can change to any value. It doesn't need any rule of increments of some certain number. But if you are changing the port priority, which is done by the command port priority, spanning tree, VLAN something and port priority, this one has to be in the increments of 16. So you type something else, it will say it has to be in the plus or minus of 60, right? If you want to change these values. For example, currently switch 1 is the root bridge. So let's start switch 2 as well, and switch 3. So let's say switch 2 and switch 3 are also up. Sorry, switch 3. So currently switch 1 is the root bridge because it has the lowest MAC address. You can confirm this from switch 2 and switch 3 as well. For example, if we take the example of this 3 switches, and let's check this out here. So you can see that switch 1, switch 2, and switch 3, they all have the same priority by default, 32768, 32768, and 32768, right? But we know switch 1 has the lowest MAC address. Let's just call it A, and switch 2 is B, switch 3 is C. So switch 1 will become the root bridge for all the VLANs, and we will check it from the example of VLAN 1, but it could be any other VLAN as well. So switch 1 is the root bridge, and that's why you see that all the ports of switch 1 are designated ports. This is designated, 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 and designated. All ports are designated. From switch 2 side, when I receive the BPDU from switch 1 on Ethernet 0/2, the initial path cost was 0. Here I add the path cost, make it 100. Same thing when I receive the BPDU on this port, the initial path cost was 0, and I make it 100 here, right? And switch 3 is also receiving 2 BPDUs, making the path cost 100. And then switch 3 is sending it further to switch 2 on these 2 ports. And outgoing port, you don't change it, but on the switch 2 side, we add the cost, so it becomes 200 and 200, right? So think about switch 2. Switch 2 has 4 ports. You can forget about these ports. Switch 2 has 4 ports, and on all 4 ports, we are receiving BPDUs. But on Ethernet 0/2 and Ethernet 0/3, we have the path cost 100. And on Ethernet 1/0 and 1/1, we have the path cost 200. So they are already out of picture. They cannot be the root ports because root port has to have the lower cost. So So either Ethernet 02 or Ethernet 03 will be the root port. But which one? We can only have one. They both have the same cost. So how do we know which one will be used? So again, we go through these four rules, right? The conflict resolution rule. Who is your root bridge? What is the path cost? What is the sender bridge ID? And if the sender bridge ID is also same, then what is the sender port ID? Sender port ID. So we can see that on switch 2, we are receiving BPDU on Ethernet 02 and 03, and both are coming from switch 1, which is the root bridge. So both BPDU claim that switch 1 is the root bridge. So we don't get the result on the first point. Second point, what is the path cost? The path cost on this BPDU number 1 is 100 versus on this BPDU number 2 is also 100. So we don't get the result on path cost. It is same, right? Then we go ahead and compare the sender bridge ID. Who is sending me this BPDU number 1? Switch 1. Who is sending me this BPDU number 2? Again, switch 1. We are just having two links, right, to switch 1. So the sender is also same of both BPDUs. So we don't get the result on the sender bridge ID also because it is the same sender. Then we come to the very last point, sender port ID. So what is the sender port ID? Port ID, if you remember, is the port priority. Port priority, which is 128 by default, and the port number, which is depending on the port that you're using, right? And we are talking about the sender's port ID, means who is sending me the BPDU. So this BPDU number 1 is coming from switch 1. So switch 1 Ethernet 02 port priority and port number are also received on this port. So what are those? Let's go and check on switch 1 on Ethernet 02. What is the values? So show explanatory VLAN 1. We can see that for Ethernet 0/2, it is 128.3. Means 128 is the priority and 3 is the port number, right? So we are receiving from switch 1 on the BPD 1 128.3, means 128 port priority, port number is 3. Similarly, on Ethernet 0/3, we are receiving 128.4, right? 128 port priority, 4 is the port number. So we are receiving on this BPD number to 128.4. So we compare these two things. First, we compare the port priority, which is same, 128 versus 128. Then we compare the port number, 3 versus 4. Lower is better, so 3 is good. So Ethernet 0/2 here becomes the root port for switch 2. That's where we get our result. So if I go to switch 2 and check the show span tree, I should see Ethernet 0/2 as the root port, right? So let's go to switch 2 and check show span tree VLAN 1. Yes, Ethernet 02 is the root port. So our hypothesis is correct, right? And exactly same thing will happen on switch 3 as well. Switch 3 will receive the BPDUs from switch 1 and also via switch 2. So via switch 2, the cost will be 200, so we don't even consider that. But via switch 1, again, we are receiving two BPDUs, one on Ethernet 1/0, one on Ethernet 1, one from Ethernet 1/0 and one from Ethernet 1/1 from switch 1 side. And we are going to compare the port priorities, which are same. Then we are going to compare the port number. So on switch 1, Ethernet 1/0 has the port number 128.5 and 1/1 is 0.6. So 0.5 wins, right? So the BPDU received from 0.5, which is this one. That means the BPDU that is received from the BPDU that is received on Ethernet 00 is the better one. So on switch 3, Ethernet 00 should be the root port. So if I go to switch 3 and check that, so span tree VLAN 1. Yes, Ethernet 00 is the root port. So our hypothesis is correct. Our logic is correct in calculating about span tree protocol, right? That means, let's say if I want to change the root bridge to switch 2, I don't want switch 1 as the root bridge. What can I do? I cannot change the MAC address, but I can change the priority, right? Priority everywhere is 32768. So if I go to switch 2 and reduce the priority from 768, then it should become the root bridge, right? So let's go ahead and try that. Let's go to switch 2 and reduce the priority. Currently, if I see the bridge ID of switch 2 is this, because priority is 3278, right? And let's go ahead and change that. So span entry VLAN 1 priority, let's say I change it to 8192, which is lower than 32768. So now what will happen if I check show span entry VLAN 1? Now it will say that this bridge is the root bridge. We have become the root bridge. And earlier you see we had some root ports, some port were blocking also. But now all ports are designated ports, right? And of course, now this will change the equation. Switch 2 becomes the root. So all the ports are designated here. Switch 2 is the root bridge, so all ports are designated. And for switch 1, the same thing will start. I will receive the 2 BPDUs from here. Both will have the cost 100, path cost 100. I will also receive it via switch 3 on 2 ports. Here the cost will be 200 from both sides. So I don't consider these. But between these two, 02 and 03, I will compare the port IDs. Port priority from switch 2 side is 128, and port number will be lower for Ethernet 02. So on switch 1, Ethernet 02 should become the root port now, right? So if I go to switch 1 and check show span entry VLAN 1, earlier you see that all ports were designated because it was root. This bridge was the root, but now it is no longer the root. You see that the root has the path cost 100 and it is connected on this MAC address, which is switch 2. And Ethernet 02 is the root port. 0. Which port is the root port? Ethernet 0/2. Right? So that way we can actually change the decision making of the switch as well. Right? So I'll send you this lab of STP. You have to do the same thing, just changing the priorities for different VLANs and see that how exactly it is going to affect who will be the root port and who will be the non-root switch, right? So that's it for today. We have understood the basics of convergence of STP. In the next session, we are going to understand what happens if there is a failure. So if there is a failure, STP has to reconverge and it actually follow a certain procedure. And we will see some security features of STP as well, right? So that's it from my side. Let me allow you to unmute. Okay, you can already unmute. So if you have any question, let me know.
No question. I was one of the most complex comps that I've ever seen, but we'll go away and read it.
Yeah. This is actually the simplest I can make it, to be honest, to break it down like this.
Yeah.
But yeah, I think after a few viewings, you will see that, okay, yeah, this, because the logic is clear, but now the things will start making more sense once you do the lab also and go through the video recording again.
No worries. No worries. So thank you very much for your time. Really appreciate this.
Thanks, Scott, and have a good day. Bye-bye.
You too. All right. Cheers. Bye.